So in case you recall, we introduced the chapter by reviewing what we have learned in Chem about thermodynamics. So we learned them about what? Energy is just equals to heat plus work. Okay. We also learned about the delta H. When if it's positive, you have an endo. If it's a negative, you have an exothermic reaction. Now, what we're trying to do is we introduce the concept with the term spontaneous. So, spontaneous process is anything that happens on its own. And I give you the classic example there that if you're not going to do anything, you're going to fail the class. Okay? So what they're trying to do is to find some sort of a physical quantity that can be related to a reaction that is spontaneous. Now, the delta H is not enough because some reactions that are endothermic are spontaneous and some reactions that are exothermic are also spontaneous. So you were introduced to this another physical quantity known as S, which is the degree of randomness or disorderliness. So what they observed, all spontaneous process usually become more disordered. Okay, so as delta S is equals to a positive value, so that means it becomes more disordered. And if you have a delta S that is equals to a negative value, then it becomes more ordered. So maybe before we continue, I'm going to use some other materials here to help you recall what we have discussed about this, what we call the spontaneous process. So this is from another book that I use. So I just want your participation here just to see if you really understand the concept, okay, that we have discussed last time. So let's try to answer this question here. So you don't have that in your material. We just have this here in this what we call slide. So predict whether the entropy change is greater or less than 0 for each of the following process. So how are you going to solve this? Freezing ethanol, what would be the delta S there? So if it's less than 0, okay, your delta S is what? Negative. If it's more than 0, your delta S is?
Positive.
So what is the delta S when you are freezing the ethanol?
Negative.
Is it negative? Okay. Anyone? Anyone else an answer? So if you're going to look at this, you have ethanol from a liquid becoming solid. So it becomes more ordered, so your delta S is negative. Now how about this one? Evaporating a beaker of liquid bromine at room temperature. What would be the answer there?
It would be
Positive.
Okay, so this will be positive. Okay, now how about dissolving glucose in water? What's the delta S there? Okay, so dissolving glucose to water. So what happened? Glucose in the solid form becoming part of the solution. So what do you think happened?
It's positive.
Okay, so it becomes more disordered. Glucose in solution form is more disordered than glucose in the solid form. Now, last but not the least, cooling nitrogen gas from 80 degrees Celsius to 20 degrees Celsius.
Negative.
Okay, so It becomes much colder, so most likely here, your gas will become what? A little bit compressed, so the delta S is negative. Okay? So do you have question when you bombarded with materials like this one? I got this from another book, but I just want to use it because we have all the time that we have. Okay? Now, the next thing that we have discussed is we can also get the delta S of a given reaction. It's just equals to the summation of the delta S of the product minus the delta S of the reactants. So I can use some example here also. This is another book. So what we have this learned from last time, we learned this from Chem 1, right? The chapter 6 of Chem 1, the conservation of energy. That's the first law of thermodynamics. So energy can be converted from one form to another, but energy cannot be created nor destroyed. And what we have learned from this chapter in Chem 2 is the second law of thermodynamics. Another way to state the second law of thermodynamics is the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So what does it mean? Okay, whatever you do, there will always be disorderliness in the universe. And they observed that all spontaneous process, the delta S always increase. Okay? So this is usually the equation that I'm trying to show you. So the delta H and later on the delta G all follow the same format. All you need to do is replace this one. So what's the difference of the delta S compared to the delta H and the delta G? You only get a value of 0 of this if you are at 0 Kelvin. Unlike the one that the delta H and the delta G has. They have values of 0 even at room temperature. So let's try to solve this one. So what I'm going to do is I'm going to supply to you the delta H, okay, or the delta S of each of the reaction that you have here. So I have here as 92.9. I have here as, my God, my eyesight is really getting worse, 39.8. And I have here as 213.6. Now come think of it. Does those values make sense? Just by looking at them.
No.
Why not? Why doesn't it make sense? Look, this is a gas, this is a solid, and this is a solid. So does it make sense that the value here is much larger than the one that you have here?
Oh,
This
yeah.
one is much bigger compared to the one that you have here. Do you see what I mean? What did we learn from this chapter? The liquid is more disordered than the solid, and the gas is more disordered than the liquid. Now, as you could see here, the gas state has the highest amount of your delta S. Now, what makes this more, we could say, made sense that this value here is much greater than this value here, although both of them are solid. Do you see what I mean? Why do you think this is much higher compared to this one, although both of them are solid? Anyone? Before you do the calculation. Do you see the difference aside from both of them being solid?
Yeah.
Is it because the one on the left has more oxygen?
So this has more elements compared to this one. So what do we know? The more elements that you have, the more disordered your system is. It's just like in real life, right? If you're single, you're fine. If you are in a relationship, you end up with some painful status known as it's complicated, right? So the same thing here. So that values alone made sense. So this one is bigger or highest because that's the gas. This one is higher than this one because you have more elements compared to this one. Now, how are we going to solve the problem? So we're going to add this, okay? And then we're going to subtract it with this one. What do you get? Before I put the other values that we have here. So the values that I have here, this is 131, this is 192, and this one is 193. So what do you get here? What's the delta S of the reaction here? 161. And how about letter B? While I put the value for letter C. So what do you have here? So this is just a review. So you have this multiplied by 2, okay, subtract by this, plus this one multiplied by 3. So what's the value that you get there? So what do you get?
587.
587. How about the others? Anyone? The others?
Wait, so you have to multiply 2 times 193
Yeah,
and then
because you have
subtract it.
2 here. And then you subtract it with the one that you have here. Since you have 3 here, you multiply that with the number given there. So what do you get? Anyone? So you get there negative 199. Now, last but not the least, so you multiply this by 2, and then you subtract it from with these values, the sum of these two values. So what do you get? What do you get from here? Is it 10?
It's -10.
So 187 plus 187 minus 131 plus 233. So this is what? 364. Just want to make sure. 131, 233. 187 plus 2. 187 times 2 minus 131 minus 233. So you got 10. Now, what do you notice with the delta S of a given material? Those are the values you can find here, this side, this area here. What do you notice about the delta S values? They are all what? Positive, right? Do you see any negative values here?
No.
No. So we could just say that all the delta S value of a given compound or elements, okay, are positive. Now, when you add them or subtract them, the value that you can get can either be what? A positive, a negative, or a positive. So what does it tell us? What does the 161 tells us here? This system becomes what? More ordered or more disordered? Anyone? In the first reaction, the system becomes what? More ordered or more disordered based on the delta S of the reaction value?
More disorder.
Okay, they become more disordered. Now the question, does that make sense? Then you have to look at the reaction. So you have your solid, and then after the reaction, you have a solid and a gas. Okay, so from 1, it becomes 2 compound. So it becomes more disordered. Now here, from 2 elements, it becomes 1, just like the Spice Girls song, 2 becomes 1. Okay, and it only means that it becomes more ordered. And the evidence for that is the negative 199 value. And to back up, why do you get a negative 199? You look at the reaction. Okay, so you have there 2 kinds of elements. They form into a compound. And if you're going to look at number, you have there 4, okay, of 2 kinds of element that reacts to form 2 compounds. Or we could say 2 moles of ammonia. Now, the last one that we have here, the entropy is just a little bit low. Okay. And it makes sense because both of them are what? 2 on both sides, and both of them are gases. The only difference, in one side, both are elements, and the other side, it's a compound. So I hope you understand this, what we call concept that we have here. Because the next thing that we're going to do is, now we have the entropy, now we have the enthalpy. When we combine them, we have now the delta G, the Gibbs free energy. Okay, and we have discussed some calculations last time that we can have the calculations of delta G from the granddaddy equation, which is this, or from the one that we have earlier, like this one. All you need to do is replace this with what? G, okay, G. We call it the Big Mama equation. And we have an equation wherein we use both of these equation, and we get a number that are close to one another. So the next thing that we're going to do now, I'm going to use the slide here because it's not, so this is the one that I said, okay? So this is the Big Mama equation, but you can also have it like this, which is the granddaddy equation. So what we said, okay, when the delta G is less than 0, we could say the reaction is spontaneous as written. If the delta G is greater than 0, the reaction is non-spontaneous as written, but the reverse reaction is spontaneous. And if the delta G is equals to 0, okay, you have a reaction that is at equilibrium. Now, I want to utilize this, what we call slide, because the material that we have don't have it. So if we're going to look at this one, if we're going to summarize, okay, this granddaddy equation, we can predict what the value of delta G based on the value of delta H and delta S. So it has here, if both of these are positive, what will happen? Because remember, we can only have delta G as negative, so that's the one that is spontaneous. And then delta G is positive, that's the one that is non-spontaneous. Now, what happens if you have both positive values here? Everything depends on what? To predict whether delta G will be positive or negative. Everything depends on the temperature. Okay? So as stated here, if both delta H and delta S are positive, the delta G value varies or depends on the value of the T. If the temperature is high, what will happen? This will become negative. But at low temperature, it is positive. Do you see the math when this becomes negative? If the value that you have here is higher compared to that one. And what makes that higher? The temperature, because there's a minus sign there. However, if you have what? This is positive and this is negative. So negative times negative will give you what? Negative times negative will give you positive. You add with the positive. So all the time, the delta G is positive. So reaction is only spontaneous in the reverse direction. And if you have a negative here and a positive here, you could say this is always a negative if you do the math. Because a negative times positive will give you a negative. You add it with a negative, you get a negative value. But if you have both of them as negative, negative here, then it depends on the value of T. The reaction would proceed spontaneously at low temperature, but at high temperature, the reaction becomes spontaneous. Or the reverse reaction becomes spontaneous. So those are the type of questions that you usually ask in your quizzes and exam. So question before I go to the original slide. Because it has a different what we call presentation, the one that we have here. So in the presentation that we have here, they put like 10 kilojoules as the number for a system to be what we call non-spontaneous. But there, if it's a negative, then that's a spontaneous. If it's a positive, then it's non-spontaneous. If it's zero, then you have a system at equilibrium. But I would suggest stick to this one. I think that's much easier to think. So that's the reason why I have to use that what we call other slides. It's from the book Chang, Raymond Chang, Chemistry. Now, if you're going to interpret, so what the hell it means? So it means you already have a way to tell if a given system is spontaneous or not. Delta H, positive is endothermic, negative is exothermic. Delta S, positive more or disordered, negative is more disordered. Delta G, negative spontaneous, okay, positive non-spontaneous. So you solve the problem that we have at the beginning of the chapter. How are we going to say if a given system is spontaneous or not? So what does it mean when you have this so-called spontaneous reaction? Remember what happened in a spontaneous reaction? It happened on its own. And if you're going to look at the reaction there in terms of this, what we call free energy, this is what you have. The free energy of the reactants compared to the free energy of the products. So what's the delta G that you will get there? It's the difference between the products minus the reactants. Since the products is less than, or the Gibbs free energy of the products is less than the free energy of all the reactants, what do you get? So usually you get a negative value. Does that make sense?
Yeah.
So if you're going to look at this, oh, okay, in that case, there's a free energy that's coming from, or there's a free energy that is being generated for the reaction to run on its own. But try to do it the other way around. What do you need for this reaction to complete? Compare it to this one and this one. Which one do you want in real life? I know you don't want that sound. So if you have a spontaneous reaction, the graph that you have there in terms of the free energy of the reactants and the products are like this one. So there is energy that's come out in the reaction, but for a non-spontaneous reaction, for this to proceed, you have to supply the energy. You have to intervene. For you to get a good score in your exam, you have to work hard, right? The question really is working hard or hardly working, especially at this time. So maybe at this time, if we're going to compare it to what is happening this week, which is Holy Week, I think you are on your way to cavalry. So after the final exam, that will be what you feel on Sunday, like a what we call resurrection or Easter Sunday, if ever you're a Christian. Okay? So you're still on the way to the cavalry at this time. So that's the reason why we don't meet. I want to rest myself, okay? And it's also Holy Week. I'm a Christian, so I think I also have the opportunity to give you the chance to rest yourself because you don't have any spring break, and I think everybody needs a break. If you don't want to break, the owl is open for you. So don't take it against me. Oh, he gave us a break. Because I'm also human. I also, what we call, has this burnout thing. So if the other course has it, then just be thankful you don't have it. Because as I've told you, which I'll ask you to vote, okay, my teaching is just like similar to those three versions of one song. So try to look at the lyric of the song as your material. And the way they are delivered, that's the teaching styles of the teachers that you have. Because later on, I'll ask you which version do you want. Because I want to see if we match. Okay? Because usually whatever version you want there is the version that want, then that means you're in the right class. But if you choose the version that I'm not really particular, most likely I will now know the problem. Why are you struggling in the course? Okay? So, how are we going to interpret this, what we call pre-energy? So as you could say, if you have a spontaneous reaction, you're producing energy. And that will be related to the next chapter that we're going to have. If you have a non-spontaneous reaction, you're not producing energy. You need the energy for the reaction to complete. Does that make sense? A non-spontaneous reaction, it will not happen on its own. So you need to charge it. You need to supply the energy. Okay? The same thing that I'm telling you, you need to work hard if you want to get an A. Oh, that's not how it is. You need to learn if you want to get an A, because you can work hard and you still don't get an A. So the what we call the secret that I have for my students to get an A is for them to learn, and the grades will come. Because if you just want to get an A, okay, you'll just be frustrated. But if you learn, if you want to learn every meeting that we have here, I can tell you the A will be much easier. Okay? Because if you just say, I want an A because I want to be this. No, that's not how it is. Okay? I have no obligations to give you an A unless you learn that stuff that you need to learn. And at that time, I have no choice. Whether I like you or not, you get an A. It's just like that. Okay? I don't like all students, but I don't use that to prevent the students from getting an A. If he got the thing that is what we call required in the syllabus for a grade of A, he will get an A. It's as simple as that. Because I was trying to be objective as much as possible. So how do we interpret this free energy? So as we could say, in a spontaneous reaction, we can use it to perform useful work. How does the battery happen? There's a reaction that happens spontaneously and it produces energy. Okay? We can also use this what we call reactions, such as how the cars are what we call happening, the combustion of gasoline to move a vehicle. Combustion is a spontaneous process. Now, we can also use spontaneous reaction to provide the energy for non-spontaneous reaction. And I'll give you an example on that in our body. Okay? Now, usually, the free energy that we have is related to what we call work. The energy that you produce, that's the one that can be used to perform work. Okay? So, the thermodynamic equilibrium constant. So now, I'm going to give you the example about that work later on. I need to use the other slide. But I want to relate this chapter with the chapter or the letter that governs this course. Okay, so if you have a thermodynamic equilibrium constant, this is also an equilibrium constant in which the concentrations of the gases are expressed either as partial pressure in atmosphere, and the concentrations of solutes are expressed as molarity. So if you have the gases, they prefer to use the Kp. If you have the solute, you use the Kc. So how are you going to write the thermodynamic equilibrium here? So what's the K for first one? Anyone? So how are you going to express the K here? So K here is what? In terms of Kp, because all of them are gases. So you're going to write it as partial pressure of NO2 squared over partial pressure of N2O4. You're not going to write it in terms of like this. So this is what we call thermodynamic equilibrium, not only equilibrium constant. There's a thing there, thermodynamic equilibrium. So that's not what you're going to do. Now, what if it's a mixture, okay, of gas and solution, just like in the second one? How are you going to write the K? Anyone? Anyone? How are you going to write the K here? So you have this, which is aqueous, so that means you have this one, and then you have this what? Gas, so you have pH2. And then this one is H plus squared. So that's how you're going to write the thermodynamic equilibrium constant. So watch for the word, okay? If it's an equilibrium constant, you can make this as H2 here, concentration of H2, but this is a thermodynamic equilibrium constant. And the next thing that we're going to do is we're relating already the delta G with what we call the K that we have learned. So what happened? How are we going to relate delta G with K? Okay, so we can get the free energy at any conditions based on the standard free energy. So when we have a standard free energy, this is at a given temperature and pressure, right? But if we want to get at any different condition, we're going to use this one. So R here is your 8.314. T here is your whatever temperature that is given. Now what is Q? So that's the one that you learned. That's the products over the reactants that you learned. And at equilibrium, we know the delta G is equals to 0, right? And Q will be equals to K. So you're going to have here another delta G. And what do we call this? I call it the Ratley equation. So you have the granddaddy, the big mama, and then you have here the Ratley equation. So what does it mean? How does it relates to your delta G and K? Okay. So what do you think is the relationship here? What's the relationship of delta G with your K value? Anyone? Can we get a relationship with the value of K and the corresponding delta G? So what do we have? If delta G is negative, what do you think the value of your K?
Positive.
Okay. Usually it's more than 1. You don't have a negative value of K, right? The choices that you have, it would be like this. Because K is equals to what? Products over reactants. So if the reaction is spontaneous or delta G is positive, so that means the written reaction will take place. So you have more products compared to the reactants. And if that happens, your K is more than 1. Now, if your delta G is what we call positive, the reverse reaction is the one that is spontaneous. So you have more reactants compared to the products. So your K there will be less than 1. Does that make sense? Hmm? And if your delta G is equals to 0, okay, you have a system at equilibrium. It's not equals to 0 here. That should be equals to 1. Does it make sense? Let's try to solve a problem here. So calculate the value of thermodynamic equilibrium constant for this reaction. So the standard energy, free energy of formation is 51.30 for NO2 and then 97.82 for N2O4. So you are asked to solve K, but the first thing that you need to do is get the delta G. And delta G is equals to what? 2 times whatever the value of this 51.30 minus 1 times whatever the value of N2O4, 97.82. And what do you get? Not that one, this one. So what do you get?
4.78.
4.78. So what can you say about the delta G? So this is 4.78 kilojoules.
That the delta G is negative.
So delta G is what? Will the reaction proceed in the forward reaction or did the reaction proceed in the backward reaction? Because we can predict the value of K based on the value of delta G. So your delta G is what? A positive. So most likely your K will be what? More than 1, less than 1, equals to 1. None of the above, all of the above. So this is a positive. So that means the reaction is not spontaneous. So most likely the value is less than 1. And the next thing that we're going to do is we're going to find that value. What do? The delta G equals to the negative RT K, the Ratlink equation. So what do we have? We calculate this one. We know this one. We know this one from the given here, so we can get the K. So if you rearrange there, you have Ln K is equals to delta G negative delta G over RT. And then I'm going to replace it with the value that we have there. So this is 4.78, but this is in kilojoules. Okay, so I have to multiply it with 1,000 joules per kilojoules. And then I'm going to divide it with 8.314 joules K mole. And then I'm going to multiply it with 25 plus 273, 298 Kelvin. So what do you get? So you will get an Ln K that is negative. So what is the value here when you do the calculation? Anyone? Hello.
What was the question again?
What's the answer here? When you do the calculation, because that's equals to the negative of all the things here.
$1.929.
Okay, 1.929. So how are we going to make it into a K? You get E raised to the 1.929. So you have their K. And that would be equals to what? Point. What do you get? 0.145.
145.
So does it make sense that the K is less than 1?
Yep.
Because that's what we predict based on the given delta G. Okay? Now, another problem that we can use here is we never have utilized the granddaddy equation. We can use it to determine the temperature where the system will be at equilibrium. So you have here sodium carbonate can be prepared by heating sodium hydrogen bicarbonate or sodium bicarbonate using here. So you are asked to estimate at which the reaction proceeds spontaneously at 1 atmosphere. So what does this mean? You have to find, okay, where the value of delta G is, we could say, equals to 0. So if this is equals to 0, what happened to the reaction? If you have delta H minus T delta S, so that is equals to 0. What happened to this reaction? You can rearrange them. You can have what? Delta H is equals to temperature equals to delta S. So the one that's being asked here is, what's the temperature for the reaction to proceed spontaneously? So what you're going to do is you set this to 0. Why 0? So that you can find the temperature that you have here. So I'm going to give you the delta H and the delta S already of the reaction after they do the calculation. So you have delta H as 129.3 kilojoules. Delta S is around 337.4 joules per K. So how are we going to solve this? So if you rearrange this one, so temperature is just equals to delta H divided by delta S. And if you're going to put the value here, you have it like this. And this one, I think you have to convert this to 0.3774 because that's the only way you can make it into a kilojoules. And if you're going to look at the unit, the resulting unit there is K. So what is K? What temperature you expect this to proceed spontaneously?
$383.
Okay, so K is 383 or Kelvin temperature, or around 110 Celsius. So before I end this chapter, there's a statement that this showed there. In fact, we use reaction to move a vehicle, or we use spontaneous reaction to provide the energy for a non-spontaneous reaction. So I want you to see a specific example in our body that allowed us this to happen. But to do that, I have to show you the other slides that we have. So I'm not sure if you're familiar. I don't know if you heard this thing before. This is how, okay, a non-spontaneous process can be run by an energy that is produced from a spontaneous process. So make the smaller weight move upward, a non-spontaneous process, by coupling it with the falling of a larger weight. So what's the one that is being discussed here? What is the energy of our body? Anyone? What is the energy? What do you call the energy unit in our body? You never learn it from me. You should learn it from what we call biology. What do you call the energy unit of our body?
ATP.
The ATP. So if you have that reaction, this is what happened. So this is the ATP, and this is the ADP. So we have a lot of phosphates in our body. That's why it's just the difference between the two is one phosphate. Now, what is this coupled reaction? Wherein we have a non-spontaneous process being run by the energy that produced by spontaneous process. What do we need to live? Anyone? What do we need to live? The basic thing that you need to live. We need what? Food, right? The question is, eat to live or live to eat? But why did I say food? Because that's where your glucose came from. So your glucose is going to be what? By metabolism broken down to CO2 and H2O. So what happened to that? You produce energy, right? So do you see a spontaneous process here? We have a big molecules being broken down to small molecules from more ordered to a more disordered. Does that make sense? Hello?
Yeah.
Okay. So when you eat the food, that's the way you produce your ATP. Your ADP is converted to ATP. Now you have the ATP, you have energy. Okay? To proceed this process. Now remember, it's usually a what? A spontaneous process if it's from more ordered to a more disordered. But for the amino acids to synthesize into protein, that is a non-spontaneous process because you have a small amino acid to produce a big protein. You following me? If you understand your biology, you understand what I'm talking about. If not, then you have to wait until biochemistry what I'm talking about. Your protein is made up of amino acid. So the usual reaction is spontaneously is protein broken down to produce amino acid. But your body is building up the amino acid to produce the protein. And how can it be done? The energy that you produce from your eating your carbohydrates, that's the one that will make the reaction run where you can synthesize protein from the amino acids. And if you're going to look at the reaction that you have, okay, so what does this mean? If you have an amino acid to produce a dipeptide, you're going to have a positive delta G, which means It will not happen on its own because the delta G is positive, so it's non-spontaneous. But if you're going to couple it with ATP and water, you're going to produce that thing. Okay? And if you're going to look at the delta G, it's -2. So the K is more than 1. So that's what we call classic example where a non-spontaneous process is being run by the energy or the free energy that was produced by spontaneous process. The spontaneous process is the glucose breaking down into your CO2 and H2O, and then you produce the energy there that will run the synthesis of amino acids into protein. Did you get that?
Yep.
Before I'm going to ask you to listen to the different version and then ask you to vote, which one do you like? And in fact, what I learned from her yesterday, she's not even making available the answers to the exams that we have. Because we're trying to resolve some things that we have before we do the final exam. So she was surprised that I'm giving the quizzes without the respondus. And then he asked me, did they get 100? And then I told them, no. So I said, what's the use of using the respondus? Even without the respondus, that my students cannot get 100. Okay. So we still don't know about the makeup, but he says he planned to do it because I told them I can prepare the final exam, but other than that, that's it. Because I'm always the one who prepared the exam. And he's the one who, what we call, check them. So I don't know if you know it. Your exam is just the same as the other section since Chem 1. The only one that is different when we are in Chem 1 is the exam that I give you before the real exam. Okay? So that's the thing that we have, what we call that came upon a meeting yesterday. So I'm going to start the next chapter, which is just electrochemistry. And this electrochemistry is just a continuation of what we have so far. Where is it? I cannot find that one. Oh, there you go. Okay. So electrochem, I think if you are going to watch what Planet of the Apes is that? Dawn of the Planet of the Apes, I think. The second one from the new Planet of the Apes movies. Okay. It depicts their two greatest contribution of chemistry in society. One is medicine in the form of the antibiotic, which was used in that movie to treat one of the characters. And the other one we could say has something to do with electricity. Okay, which they use there from the not geothermal, the hydro plant. Okay, the water, electricity from water, just like Niagara Falls. So the idea that you have there that the electrochemistry is quite new. When did it start? 1800. Okay, and I don't know if you're fun with literature. Electrochemistry has an indirect, we could say, history with, is this the spelling of Frankenstein? Because they're trying to debunk some theory that they have there, that you can turn an inanimate object into animate object, or dead people, by applying electricity, you can make it alive. That's the basis of Mary Shelley's Frankenstein novel. Okay? But during that time, a guy that also lives by the name of Michael Faraday is trying to see how he can use electricity. Now, what do you think the basis of Frankenstein? An Italian scientist by the name of Luigi Galvani, he applied some current in this dead frog animal, and they see it's moving. So that's the, we could say, scientific basis of Frankenstein during that time. But what Michael Faraday is trying to do there is, can we utilize some spontaneous reaction that produce energy and light it up? So imagine if you live around 1800. Okay? What is the source of your lighting? Most likely you have what? Candle? And then you have this what power, the power wars or the current wars, right? You have an AC versus DC. Now, AC DC is the name of a bond, a metal bond. So you have an alternate currents versus a direct current. Who's the one that is the, usually there are a lot of people, but one of the things that involved there is what? Thomas Alva Edison, the wizard of Waverly Place. Is that Waverly Place? Whatever is the one that he has there in New Jersey. So during that time, they preferred the direct current. And the direct current right now is what? What's the classic example of a direct current? Anyone? Battery is a classic example of a direct current. But what we have in terms of electricity right now is the alternate current. Before they have a direct current. Okay. So when we're talking about electrochemistry, it means two things. It can mean electricity from chemistry or electricity used to run chemistry. So it all involves with this so-called redox reaction. What is redox reaction in 2 words? Most likely you will answer me this one. What is redox reaction in 2 words? Anyone? Hello?
Oxidation reduction.
I told you, that's what you have, but that's not what I'm looking for. Okay? What is redox in 2 words?
Gain or loss?
There. Redox is just electron transfer. Okay? So when you have an electron transfer, you gain or lose, you gain and lose an electron. You lose an electron, somebody will gain it. Okay? And in this, what we call electrochemical processes, there are 2 things that happen. Either the energy is produced by a spontaneous reaction, or you need electrical energy to cause a non-spontaneous reaction to occur. So you have a spontaneous reaction, they produce electricity or energy, or you use energy to run a non-spontaneous reaction. That's what you're going to do in the last experiment. Okay. Now, if you have what we call the redox reaction, synonymous to this is the so-called oxidation number. So we're just reviewing here stuff that we already obtained in Gen Chem 1. We can only identify, or we could say determine if a reaction is a redox reaction if there is a change in the oxidation energy. Okay, so we can define here reduction and oxidation. So what's the acronym that I gave you in Gen Chem 1 to know if it's a reduction or an oxidation reaction? Anyone from my previous Gen Chem 1?
The line says GR.
What's the acronym that I give you? Anyone? I'm going to get back the A that I gave you. Okay. You have the Geroa and Leora. So when we say Geroa, that's gain electron, which means it's reduced or undergo reduction, and it serves as an oxidizing agent. If you have Leora, that means you lose electron. That means you undergo oxidation, and you act as the reducing agent. So this is still powerful or helpful for you at this time. Okay. Now, if you have here a reaction, the first thing for you to determine is which one is reduced and which one is oxidized. And one way to do that is using the oxidation number, which we're going to review before we answer this one. So what is this so-called oxidation number before we come back here? So the oxidation number that we have, this is the charge the atom would have in a molecule or an ionic compound if electrons were completely transferred. This can be what we call best done if you analyze, okay, the given oxidation number. If the analysis will not be helpful, then memorization is the next one. Because as much as possible, I don't want to teach memorization. I want my students to analyze the thing. The same thing that I have a different style in the lab. In the lab, I want you to learn skills. Okay, that's why I'm a little bit strict in the lab. That's why the email that I emailed to you, my lab students, I mean it. Because we have 2 long experiments next week. And if you're coming to the lab, you're not ready because you have work, okay? You slept or you arrive at your home at 2 o'clock, I would suggest don't go. Don't come to the lab. I'll just give you the data, okay? Because when a student comes to the lab, I expect them to know what to do. Because I'm not going to spend my time preparing those materials if the students don't use them, okay? So the 2 experiments that I have, as much as possible, when you arrive there, you do the experiment and get the hell out of the lab so that the second batch of students can perform the experiment. So I will not tolerate any chit chat during that time, next Monday that we have. But this is to my lab students, because we're going to do 2 experiments next meeting, the 22 and the 23, to end the lab course, okay? Because this is what you're going to do in the lab, the terms of what we call reduction, the terms of this electrochemistry. So oxidation number, if you cannot analyze it, memorize. The first thing that you need to do, the oxidation number is always 0 if you have 3 elements. So what are these 3 elements? The one that you find the element in nature. A sodium metal, a beryllium metal, a potassium metal, a lead metal, a hydrogen gas, oxygen gas, and a phosphorus. They all have 0. And then the next thing that you're going to do, whatever the charge that they have, most likely that's the oxidation number. So if you have an Li plus, lithium ion, an ferric ion, ferrous ion, oxide, then whatever the charge, that's the oxidation number. And the thing is, oxygen, most of the time, it's -2, except when it is a peroxide, where it becomes -1. Hydrogen, most of the time, +1, except when they are what we call a hydride, or when they are combined with the metal, wherein it becomes -1. Okay? Now, group 1A metals, group 2A metals, whatever the group number that they have there, okay, usually when you combine them with another, we could say element, okay, the group 1 serve as cation will be +1. The group 2 that will serve as cation will have a +2. And the fluorine that will serve as anion, which is group 7, you subtract it with 8, you get a -1. The same thing with oxygen, okay? When it serves as anion, it's in group 6, it acts as an anion, you subtract it with 8, you have a -2. And then the thing that you need to remember, whatever the sum of the oxidation number of all the atoms in the molecule or ion, that is equal to the charge of the molecule or ion. So what does it mean? Okay. Some elements, they have their fixed oxidation number. Some elements, they have more than one oxidation number. Oxygen can have more than one oxidation number. Now, oxygen will always have what? -2 and what we call -1. So all you need to do is look at the charge. If the total charge, let's say, is just like this, so that means the charge is 0. So if you add all the oxidation numbers of all the elements there, that is the total number. And I think the example that I have here is this one. Identify the oxidation number of all atoms in bicarbonate. So if you're going to look at this, which one is given? You have hydrogen there, +1, oxygen -2. So you have here +1 plus C plus 3 times -2 equals to -1. So if you're going to have this, this is 1, this is what? 3 times -2, -6. So you have here -6 plus 1, you have C minus -5 equals -1. So what do you get? So you move that -5 on the other side. So you have here C equals to -1 plus 5 will give you +4. And there's always a question about that in your exam. And I always expect my student to know that. Okay? So let's go back now to our problem here. So let's say we don't know this one. So we're going to assign the oxidation number. So magnesium is what? A metal. So that's an elemental form. So you have there 0. Oxygen is as is. So you also have it as 0. But this one, when they form, so this is a cation, group 2 1A or group 2A. So you have +2. And this one, -2. So the next thing that you're going to do, the changes in the oxidation number there. So magnesium from 0 to +2, oxygen from 0 to -2. What happened here? Did they lose or gain electron?
Lose.
Okay. So you lose your electron here. That's why you become positive, because you lose some negative thing. Now, on the other hand, your oxygen from 0, it becomes more negative. So that means it gained electron. So you could say this one is oxidized and this one is reduced. Because I think that's what we have here. Why did it oxidize? Because it used electron. Why it is reduced? Because you gain electron. So that's the first thing that we're going to do when we resume our class next week, when we do what we call balancing redox reaction. So as I promised, the chapter 17, I'm going to move it next week, next Tuesday. The chapter 18, I'm going to move it next Thursday. So I will end up my class here. Okay, if you have any question, you can remain. Now, I don't know about the honor student, if Mohini talked to you about, if I can see you tomorrow during the office hour. You can just log in there. Okay.